Calculus deals with limits, and at this point we're going to see a couple of limits that involve trigonometric functions. The limit as x approaches 0 of the sine of x over x is equal to 1. This isn't automatically obvious because if I substitute 0 in place of x in the numerator and denominator, I get 0 over 0. We'll see where this comes from in just a minute, but in the meantime, another trigonometric limit is that the limit as x goes to 0 of the cosine of x minus 1 over x is equal to 0. Again, direct substitution would give us 0 over 0, and so this isn't immediately obvious. I'm going to label these 1 for the sine function and 2 for the limit with the cosine function, and we're going to see where these come from. So the proof of 1. Let's start with a quarter of the unit circle in the first quadrant, and I'm just going to put a point on the unit circle. We're going to call it xy, and associated with that point is an angle theta, and so that we know that the x-coordinate is the cosine of theta and the y-coordinate is the sine of theta. Now I'm going to put a blue triangle inside the unit circle with its with one vertex at the origin, one vertex at the point xy, and one vertex at the point 1, 0. The area of that blue triangle, well, the area of a triangle is 1/2 AB times the sine of the angle between them. Since the radius is 1 and that happens twice, the area is equal to 1/2 times 1 squared times the sine of theta. When we identified this angle theta, we also created a sector of the circle. Remember, a sector looks like a pizza slice. And the area of this sector is 1/2 r squared theta, right? So in this case, it's going to be 1/2 1 squared times theta. Now I'm going to move this label out of the way because I'm going to make another triangle. This one is going to use the angle theta, and it's still going to have a vertex at the point 1, 0, but now this is going to be a right triangle. Had to fix that up a little bit. Now, if I knew the height of this right triangle, then I could find the area of the green triangle and say that it's like 1/2 base times height. Well, the base is 1. Let's figure out what the height is. Actually, you could stare at this for a while and try to come up with the height, but I'm going to go ahead and tell you that the height is equal to the tangent of theta. Now that sounds like magic, but if you think about a right triangle, the tangent of theta is the length of the side opposite over the adjacent side. And the adjacent side is equal to 1. So the tangent of theta is equal to h over 1, which means that h is equal to the tangent of theta. Again, kind of stare at that for a little bit and then it'll make sense. So the area of the green triangle is 1/2 times the tangent of theta. Now, why am I talking about all these areas of triangles and the sector? Well, look, we know that the area of the blue triangle is smaller than the area of the sector because the blue triangle is inside of the sector. And the area of the green triangle is bigger than the area of the sector because the sector itself is inside the green triangle. So now I have an ordering of these areas, and I have these areas expressed in terms of theta. So 1/2 times the sine of theta is less than or equal to 1/2 of theta, which is less than or equal to 1/2 of the tangent of theta. The tangent of theta I'm going to write down as the sine of theta over the cosine of theta. At this point, I'm going to multiply all three parts by 2 over the sine of theta. I know it doesn't make a lot of sense what I'm doing, but just try to follow the steps along and then we'll get to a result. So multiplying by 2 clears the fractions. Dividing by the sine of theta gives me 1 is less than or equal to theta over the sine of theta, which is then less than or equal to 1 over the cosine of theta. At this point, I'm going to remind you what it is that we're doing. We're finding a limit of something that looks like sine of x over x. Here I have theta over the sine of theta, so I can take a reciprocal and get something that looks like what we're after, right? So if I take a reciprocal, I end up with sine of theta over theta in the middle of the inequality. But then, folks, if I find reciprocals of all three sides of all three parts of an inequality, the inequality symbols themselves reverse. Think about this. 2 is greater than 1. If I find their reciprocals, 1/2 and then 1, I see that 1/2 is smaller than 1, right? So the inequality symbol reverses. So 1 is greater than or equal to the sine of theta over theta, which is in turn greater than or equal to the cosine of theta. Let's go back to what it is that we were talking about. It's a limit as x goes to 0 of the sine of x over x. Now, for our work right now, theta is positive. So when I find the limit, it's going to be a one-sided limit. But I can apply a limit to all three parts of this inequality. And when I do, what I see is, as theta approaches 0, the limit of 1 is 1. As theta approaches 0 from the positive side, the limit of the cosine of theta is also equal to 1. Since the limit as theta approaches 0 from the positive side of the sine of theta over theta is between 1 and 1, by the squeeze theorem, the limit as theta approaches 0 from the positive side of the sine of theta over theta is equal to 1. As it turns out, the sine of theta over theta is an even function. That is, the sine of negative theta over negative theta is equal to the sine of theta over theta. It follows that the limit as theta approaches 0 from the negative side of the sine of theta over theta is also equal to 1. So we can finally say that the limit as theta approaches 0 of the sine of theta over theta is equal to 1, as we said. And we're going to use that for the proof of 2. But we're going to do that in the next video.